Suppose we consider a finite dimensional vector space V, ঠিক আছে? Then you can, then if we let and suppose phi be a bilinear form on V, then one can have this results that phi is non-degenerate if and only if for a given linear functional T on V, there exists a unique vector x belongs to V such that you can represent T as phi of x comma y for all y belongs to V. Okay, that is T is actually the function phi x comma dot. Okay, so if phi is degenerate, then for a given linear functional, that is if T is in the dual space of V, then there exists a okay, not in the dual space. So for a given linear functional T on V, there exists a unique x such that Ty equal to phi xy. Similarly, in a similar way, you can also say that phi is non-degenerate if and only if there exists, if and only for a given linear functional T on V, you can find out a unique vector y belongs to V such that T of x can be written as phi of x y for all x belongs to V. That is, T will be represented as the map phi dot comma y. Okay. And number 3, if phi is non-degenerate, then for any linear map T from V to itself, you can find out a unique linear map denoted by T star from V to itself such that phi of Tx y is phi of x comma T star y. is true for all x comma y belongs to V. So if phi is degenerate, then for every linear map you can find out a unique linear map T star satisfying this property. And this T star, as it is unique, so T star is called the adjoint of T. Relative to the bilinear form phi on V. So for a given non-degenerate bilinear form, every linear map has an adjoint, okay, T star. Now what is the proof? Now it should be noted that if you look at the definition of the non-degenerate bilinear form, then you will see that phi is non-degenerate if and only if the map that has been defined before, that is psi L, the map psi L from V to V star defined by psi L of x is phi L x dot defined by psi L of x is phi L x dot for all x y belongs to V, for all x belongs to V, where psi L x of y is phi xy for all y belongs to V. So this map psi L is going to be 1 1, as because the radical is singleton theta, right? As the radical is singleton theta, right? So, okay. Okay. Now, since V is finite dimensional, then you can prove that its dual V star is also finite dimensional. Okay, and for this reason, so since this map is 1 1, so it is 1 2. So psi L is on 2 if and only if psi L is 1 1. So in our case, this is on 2. Now what does it mean by the on 2ness of psi L? So that is for a linear functional. So for a linear functional taken from V star, you can find out. Now since the map is 1 1, so the existence of the vector is unique. So there exists a unique x, right, such that psi l x must be t. Okay, that is, now what is psi l x? Psi l x is phi l x comma dot is t. Okay, but that means, so this is equal to, so ty is phi l xy, so it is phi xy for all y belongs to p. So this proves our first result, and similarly we can take care of the second one also by applying the same arguments, just considering the right radical, right. Okay, now for the third one, so similarly, okay, 2 follows by considering the map psi r. Okay, now you have to consider the case of 3. Okay, so it has been given that phi is non-degenerate. Okay. Now for a vector y belongs to v, okay, we define a map. So you choose a vector y from the vector space v, and then with respect to this y you can define a map capital F from v to f by capital F of x is phi of tx comma y, okay, for all x belongs to p. So for this y you can define this map f. Now it should be checked that this f is a linear map. Check. F to linear. Okay. So,
Hi, sir.
f is a member of V star. Now by applying 1, you can find out, so f belongs to V star, which implies that for this f you can find out a unique vector y star belongs to phi, such that f of x is phi x y star for all x belongs to phi by applying, okay, by applying 2, okay, by applying 2. Okay. Okay, so this now, so for a given y you can have a unique y star. For a given y belongs to v, by means of this map, linear map f, so via this map you can get a unique vector y star in v. So that means, so somehow there is a correspondence between v to v via this f. So this induces a map denoted by T star from V to V by T star of y equal to y star for all y belongs to V. Okay. Now let us check whether this T star is again a linear map from V into itself or not. So T star is linear as because phi of Tx comma y1 plus y2. Okay, so this is equal to yeah, okay. Okay, I should note it down here. Okay, so fx is phi x y star, and also as by definition fx is phi txy. So from this, so phi of txy equals to phi x y star, but what is y star? Y star is t star y. So phi x t star y. Okay. So therefore you can apply this equation. So this is phi x t star y1 plus y2. Okay. So this implies that is, so phi x t star y1 plus y2 equals to phi of tx y1 plus y2. So you can expand it as because this is a bilinear form. So this is tx y1 plus phi of tx y2, and then again it is phi of x t star y1 phi of x t star y2. So therefore this again phi of x, so t star y1 plus t star y2. Now this equation will be valid for any x belongs to P, and so this t star of y1 plus y2 is actually t star y1 plus t star y2. So this proves that t star is additive, and in a similar way one can also show that. So similarly, it's not very much tough to check that t star of alpha y is alpha t star y for all scalar alpha belongs to F and for all vector y to P. So therefore t star is a linear transformation. So this proves that t star is a linear map transformation from V into itself. Okay.
Yes, sir.
Okay. So this says that this theorem is very important because, so if you have a non-degenerate bilinear form, then for every linear map will give you a unique linear map, that is the adjoint of T. Now properties of T star. Okay, so suppose, so number one, T plus U star is T star plus U star if you take any two linear maps from V, that is if you take home V comma V. the set of all linear transformations from V into itself.
So T plus U to.
T plus U. Yeah.
Hmm.
Similarly, Tu star is U star T star for all T comma U belongs to this set. Similarly, if you take any scalar alpha and T, so alpha T star is alpha of T star for all T belongs to this. And number 4, if you take the adjoint of the adjoint of T, then it will be T. Okay. So the proofs are very simple, just using the equation that has been stated above, that is this one. So using this you can get every result. Okay, so suppose number 1, so for all x belongs to V, so if you take phi of T plus U x comma y, then it will be your phi x T plus U star comma y. Okay, so that means, so therefore, so phi of x T plus U star y is phi of, so now T plus Ux comma y is, so it is Tx plus Ux comma y, so therefore it is phi of Tx comma y, phi of Ux comma y, so that means it is phi of x T star y, phi of x U star y, so therefore it is phi of x T star y plus U star y, so ultimately you will get T star plus U star of y. This is true for all x comma y belongs to V. So therefore T plus U star is equal to T star plus U star. So using the same process you can easily prove that 1 and 3. Okay, and for 4, so 2, 3 are left as an exercise. Number 4, so phi of Tx comma y, so it is phi of x T star y, so definitely from this one again you can apply that T, sorry, so start from this T star, then you will have T double star x y. Now this is true for all x comma y belongs to V, so therefore Tx equal to T double star x for all x belongs to V, so therefore these two functions are same. So this proves 4. So these are the very nice properties of adjoints. Now we are looking for the linear maps having adjoints which is uh, a linear map itself, that is they are called self adjoints. So a linear map or a linear operator T on V is said to be self adjoint with respect to the given non-degenerate bilinear form on V if its adjoint coincides with itself. So if T star is T, then we call them as self-adjoint operator. Note that if W be a subspace of V and phi be a bilinear form on V, then phi restricted to W is again a bilinear form on W. Okay, and not only that, since if phi is non-degenerate, so is phi restricted to W. Okay, and okay, so and if phi restricted to W is non-degenerate, so suppose you have a bilinear form where you find that for a subspace W, phi restricted to W is non-degenerate, then this W is defined to be a non-degenerate subspace, a non-degenerate subspace of the vector space V. Also, we can observe that for this for a given W, subset of V, WL perf defined to be the set of all X belongs to V, satisfying that phi x W equal to 0 for all W belongs to capital W, and in a similar way you can define the right orthogonal complement as set of all Y belongs to V such that phi of W comma Y equal to 0 for all W belongs to capital W. Okay, now if W is a non-degenerate subspace, then the intersection of W with any of these sets are singletons, singleton theta. Okay, and with respect to this observation, so given a non-degenerate subspace W, what you will have for the vector space, that vector space can be decomposed into two parts, that is, one is W and another one is either WL perf or WR perf, that is, V will be represented as a direct sum of W and this or W and this. Okay, so the theorem says that let phi be a bilinear form on V and over some field F if W be a non-degenerate subspace, of V, then one can decompose V as a direct sum of W, WL perf, or W direct sum of WR perf. Okay. Now, why it is true? What is the scheme of the proof? Now, since W is non-degenerate, so you are going to have this observation, that is W intersection WL perf is singleton theta, or and W intersection WR perf is singleton theta. So that means the addition of these two subspaces are direct. The sum is direct. Okay. So note that W plus WL perf or W plus WR perf are direct sum, right? Direct sum. Now we consider the map phi L from V to, we take the W star, okay, defined by, so phi L x is phi L x comma dot restricted to W, okay, or you can say that phi x comma dot restricted to W, okay. So you can prove that this phi L is a linear map from V into W star, and since this is a linear map from V into W star, so dimension of V must be equal to the dimension of the image space of phi L plus dimension of kernel of phi L, right? Just if you recall the
dimension of বললাম এটা
image space of phi L and dimension
আচ্ছা
of kernel of phi L, এই যে rank nullity theorem যেটা,
হ্যাঁ হ্যাঁ
ঠিক আছে, এখান থেকে আমি বলতে পারছি। Now take, so let F belongs to W star, F belongs to W star. So we need to check that this phi L is onto. That means image of phi L will be the whole W star. So for this reason, let us suppose that F belongs to W star. Now since W is non-degenerate, so the restriction of phi to W is non-degenerate as per definition of non-degenerate subspaces, that is on W, is non-degenerate on W, and therefore, so this map is a non-degenerate, so this is a non-degenerate form on W. So you can apply the previous theorems for this map, for this form, and so there exists a unique vector W belongs to capital W such that f of x equal to phi W comma x sorry, I should write it as phi y. Yeah. For all y belongs to W, that is, so this is actually phi L W comma y. Okay, so that means f can be written as phi L W comma dot. Okay, W
Yes, sir.
dot. So okay, dot, yeah, restricted to W, because this is true for all y belongs to this. ওকে, তাহলে এফটাকে তুমি এইভাবে লিখতে পারছো, তার মানেটা কি দাঁড়াচ্ছে? Yeah, so that means it is so therefore, so this is your, so as per definition of this map, so this is your phi L W. Okay, so therefore image space of phi L is W star. This implies, so dimension of V equals to dimension of W star plus the kernel is actually WL perp, so it is WL perp, or you can say that it is dimension of W star plus dimension of WR perp. Okay, yeah, but dimension of W star is equal to W, dimension of W, so therefore it is dimension of W plus dimension of WL perp, or is dimension of W plus dimension of WR perp. So this proves that V is the direct sum of either this, or you can write it as this. নন ডিজেনারেট সাবস্পেস যদি হয়, so you can decompose V as a direct sum of W plus WL perp. Okay, okay. Now observation, okay, now if you consider symmetric bilinear forms, symmetric bilinear forms, then we can define, then one can talk of orthogonality of vectors. In V by means of the following way. that is for x y be two vectors in V, x is said to be orthogonal to y if phi of xy equal to 0, equal to 0, which is denoted by x part y. Okay, and it should be noted that the relation of being orthogonal defined on the vector space V, orthogonal defined on the vector space V is a symmetric relation. As because x is orthogonal to y if and only y is orthogonal to x, as because you have considered a symmetric bilinear form relation, that is x is orthogonal to y if and only if y is orthogonal to x. And also, as you have considered symmetric bilinear form, so also if W be a subspace of V, then the sets, that is WL perp and WR perp, they will coincide because the form is symmetric. So then WL perp and WR perp both are same, and you can denote it by W perp, which is defined to be the orthogonal complement. Orthogonal complement of W with respect to a given symmetric bilinear form phi defined on V. Okay. Okay. Now, if we let V to be a finite dimensional vector space over some field F, where what some field F having dimension n, suppose having dimension of V is n, where we have defined a symmetric bilinear form phi. Then a basis, suppose you take u1, e2, en, because its dimension n. So a basis e1, e2, en is defined to be an orthogonal basis of V with respect to the bilinear form phi if phi of any pair of vectors taken from e1, e2, en, that is ei, ej, must be 0 for all I comma j where I not equal to j. So a basis u1 into en in V is defined to be an orthogonal basis of V if the functional value of phi of any pair of vectors taken from u1 into en, distinct vectors ei, ej, if this is phi, this is 0, sorry, 0. Okay. Now let us introduce the notion of quadratic forms analogous to the notion of norms on a vector space induced by inner product. So suppose you have now, if phi be a symmetric bilinear form, that is, okay, then we can define a map denoted by Q from V to F by means of the following definition, that is Q of vector x is phi xx. This is true for all x belongs to. Okay. So given any symmetric bilinear form, you can always define this kind of map, and this map is enjoying these following properties, that is, suppose you take two vector x and y, so qxy must be phi of x plus y, that is phi of xx, phi of xy, phi of yx plus phi of yy, right? So that means, so this is qx and this is qy, and since the form is symmetric, so this is 2 qxy. Okay, and this is true for all x comma y belongs to V. So now, so 2 qxy, I'm sorry, this is phi.
স্যার ওটা কিউ এক্স ওয়াই সমান ফাই এক্স ওয়াই এটা হবে তো?
না, phi xy,
হ্যাঁ, ওটা 2 phi xy তো হবে।
2 phi xy equal to qx plus y minus qx minus qy. So this is true for all x comma y belongs to V. Now if we let characteristic of the field is not equal to 2, then phi of xy can be written as half of qx plus y minus qx minus qy. Okay, so this is true for all x comma y belongs to V. Okay,
এটা কি লিখেছেন লেট, এটা ক্যারেক্টারিস্টিক নাকি?
characteristic of the field is not equal to 2. 2 হয়ে গেলে তো এটা 0 হয়ে যাবে,
0, হ্যাঁ।
ভাগ করতে পারবো না, ঠিক আছে? In that case q will be additive. Not only that, if characteristic of f is 2, then what will happen to q? for any two vector, for any x, suppose you take qx x plus x, then that will be 2qx, but that will be 0. So the quadratic form will become the 0 map. Okay. And number 2, q of lambda x. This is phi of lambda x, so that is, so this is lambda square phi of xx, so that is lambda square qx, and this is true for all vector x from V and for all scalars lambda. Okay, so this is called the quadratic form q defined on a vector space V with respect to a symmetric bilinear form. Symmetric bilinear form phi on V. যে কোনো একটা সিমেট্রিক বাইলিনিয়ার ফর্ম দেওয়া থাকলেই তুমি একটা কোয়াড্রেটিক ফর্ম ডিফাইন করতে পারো। যেমন হচ্ছে তোমাকে যদি এটা ইনার প্রোডাক্ট দিয়ে দেয়, তাহলে তুমি একটা কোয়াড্রেটিক ফর্ম ডিফাইন করতে পারো। কি হবে না, কিউ এক্স ইজ কি ডিফাইন করবে?
হ্যাঁ,
নর্ম এক্স স্কোয়ার, তাই না? নর্ম এক্স স্কোয়ারটা, ঠিক আছে? সো জেনারেলি, so in general, if we consider a field having characteristic of a field f having characteristic of f not equal to 2, then we can define the following. What is the definition? So a general quadratic form, so a quadratic form on a vector space V is a map q from the vector space to the field f such that the first property is q of lambda x should be lambda square qx. This is true for all x belongs to V and for all lambda belongs to f. And number 2, if you define a map phi xy by means of this expression, that is half q x plus y minus qx minus qy, then this map, then phi from V cross V to f, so this phi will become a symmetric bilinear form on V. So this, the phi will be a symmetric bilinear form on V, that is phi in this set. Okay, so if this q will satisfy these two axioms, then that type of map Q will be defined to be a quadratic form on a vector space V in general. And for example, if you have a symmetric bilinear form, then you will always have this kind of quadratic forms. Okay. Okay. So okay. So note that if we denote the set of all quadratic forms defined on a vector space V, the set of all quadratic forms on a vector space V over F with the assumption that the characteristic of the field is not equal to 2, then this set will form a vector space over F. Okay. With respect to usual addition of maps and scalar multiplication. So okay, so from the above discussion, you have this fact that suppose you take a vector space, so let V be a vector space over a field F with assuming that characteristic of F is not equal to 2, then the map F from the set of all bilinear forms, symmetric bilinear forms on V to the set of all quadratic forms on V. So these two are so F is a map from this set to this set defined by F of phi equals to the quadratic form Q, and suppose you indexed it by phi, okay, where Q phi of x is phi of xx for all x belongs to P. So this map F is going to be 1-1 correspondence. Okay.